Woo! All right, here we are. Now, today's do now is going to be quite enjoyable. But I want to make sure you guys get what you're doing. Look at this. Put that up there. Okay. What you're given here, you're actually given, we're going to come up with a graph from the information given on in this chart here. Now, there are actually several points that you're going to be able to plot. Can you count how many points on the graph? Oh.
Please excuse this interruption. Please allow all varsity football players and TO officers to the gym at this time.
You have to leave. Yeah. No, I know. You're the. I think she's the quarterback. We'll see you later. Okay. So, guys, how many points? Because we're going to wind up graphing this. Let's see how many points we have to start with. Take a look at the information given. I'm not going to say anything else. Just tell me how many points there are. They're actually given on the graph of the function.
3.
Someone say there are 3 points?
3.
I think they're 3, right? There's 0, 0, 1, -3, and 4, -9. Today's the 4th. All right. So we have 3 points, but what I want you to do, first I want you to fill in the information for each of the intervals between the points. Wow, Jillian's very disruptive today. Jillian is very disruptive. So anyway, on this first interval from -infinity to 0, we're told that the first derivative is positive and the second derivative is negative. Tell me about this graph on that interval. First derivative is positive. What's that telling you? Okay, increasing for the first derivative being positive. Okay, so we know our graph is going to be increasing here. Second derivative is negative. What's that telling us? It's concave down. So we know that that part of our graph is going to be increasing and concave down. Now what I want you to do is fill out the same information. I would first work on the intervals and then figure out what's going on at each of the points. You know, like figure out next what's going on from x = 0 to 1 using the sign of the first and second derivative. Do all that and then see if you can figure out what's going on at each of these given points. They're kind of special too. Yeah, they are. They are very special. I'm going to pause and neat just to get the shape. All right, so we're back. All right, on the interval from 0 to 1, both the first and second derivative are negative, so the function is doing what? Decreasing and concave down. You got that? Okay, the next interval from 1 to 4, first derivative is negative, second derivative is positive. What's going on with the graph? Is your hand being raised or show me the shape? Okay, yeah. Decreasing, concave up. Nice. Fine? Good. Nice. Increasing and concave up. Concave up. Now, I'm going to go back and look at each of the points that we have here. At the point 0, 0, there's different ways you go about looking at this. You might notice that the first derivative is going from positive to negative. Or you might notice that, oh, the first derivative is 0 and the second derivative is negative. But either way, what does that tell you is going on at 0? A max, right? The first derivative is changing from positive to negative. That's one way we know it's a max. The other way, we know that the derivative is 0 and the second derivative there is negative. So that's like what we did yesterday. So we got a relative max. At the point 1, -3, what's going on there? Point of inflection because, okay, well, it's the second derivative's changing sign, okay? It's going from negative to positive. So we have a point of inflection. At the point where x = 4, what do you think? Do we have a point of inflection? Do we have an extrema? Okay, John? We have a min because nice. The first derivative changes sign from negative to positive. Good job. So, with these points, and we know the behavior between the points, we should be able to come up with a nice little graph. Okay? And if you plot the points, because I don't feel like going back and forth, sorry. So, I know it's bad I'm doing that, but like, look what if you would start by plotting the point 0, 0, 1, negative 3, and 4, negative 9, right? Now, from negative infinity to 0, we said the graph was increasing and concave down. You might have drawn yours out here. All right, we don't know exactly what, we don't have any points to go through, but yours should have the same shape. So it's increasing and concave down from negative infinity to 0. Then from 0 to 1, we said the graph was decreasing and concave down. That's why it looks like this here. There you didn't really have much play, you know, because you had to get to that other point. Then from x equals 1 to 4, we had to draw a graph that was decreasing but concave up. And then when x was greater than 4, we had to draw a graph that was increasing and concave up. So you get something that looks kind of like that? Yep, yeah. Questions on that one? All right, today, you know, it hasn't been that long that people have had graphing calculators. And if you think about it, if you went back 100 years, not even that far, even if it was like 50 years, and someone said, hey, here's an equation of a function, graph it. What would you do, you know? You didn't have a calculator to graph it. You just maybe pick some x values, figure out the y, and plot a few points. But how would you know how it's curved, you know, in between the points? You'd have no idea if you're missing some big features. And with calculus, we really can come up with some beautiful graphs. And that's what we're going to do today. Oh, I have to go over the homework, sorry. So the first one worked out great. We said we have this other way to find extrema. If you want to find the extrema of a function, yes. Oh, that was bad. Excuse me, thank you. Okay, so if you want to find the extrema using the second derivative test, you find out where you have horizontal tangents. You set the first derivative equal to 0, and that occurs at negative 2 and 1. And then you substitute each of those into the second derivative. And as long as you get a negative or a positive, you've got them. So you should have, there's a max at x equals negative 2 and a min at x equals 1. Did you get that? Oh, I didn't do the fill-ins with the words, did I? I'll do those. I will just say those. On the front page of the homework, before we got to 1, there was just like a fill in the blanks. Okay, if I look at that, okay, for the first set, it said, if the first derivative at c is 0, then the slope is 0 at c. The second derivative is positive, then the graph is blank near c. What'd you fill in there? Concave up near c. Therefore, c is a local min. And then that second part, it says, if the first derivative at c is 0, then the slope is 0 at c. And if the second derivative is negative, the graph is concave down near c. Therefore, c is a local max. Okay. So I didn't fill that in. Okay, now, so the second derivative test for extrema worked great on number 1. We get to number 2, and it worked fine to get one of the extrema. You set your first derivative equal to 0. You got x equals 0, x equals 1. When you put the 1 into the second derivative, it was positive, so you know you had a min at x equals 1. But like the 0, when you put that into the second derivative, you should have got 0. And when that happens, the second derivative test is inconclusive, and you just got to go back to the good old first derivative test for extrema. You make your first derivative sign chart. Because if you just relied on the second derivative test, you wouldn't know what was going on at 0, because it made the second derivative 0 also. But when you did make your sign chart for the first derivative, you see you have a max at 0. Alrighty? And then the fourth one, which I know is confusing for some people, the way it was worded, I guess, you really wanted to just make a sign chart for the first derivative. Like, they gave you all this information about the first derivative. They told you where it was positive, where it was negative, and they told you where it was equal to 0. That was at -2 and 0, and where it didn't exist. Because where a derivative is 0 or doesn't exist, those are the critical points. And if you made your first derivative sign chart, you could just answer the question, where are the extrema? Well, they would be at -2, you've got a min, because it changes from negative to positive. At 1, there's a max, because the derivative changes from positive to negative. And at 1, there's a min. I wrote them in the opposite order, but yeah. Okay. Now, if I tried to figure out the extrema using the second derivative test, I would have only looked at the values of x where the derivative was 0, namely -2 and 0. If I tried to plug -2 into the second derivative, I know it's positive, so I would be able to figure out that I had a min at -2. But at 0, the second derivative is 0 also, so I wouldn't have been conclusive. So if I tried to use my second derivative test to find the extrema in this case, the only one it would have found was the x equals -2, there's a min. So the first derivative test worked fine. I just wanted you guys to find the extrema. And then if you make a sign chart with the information that they gave for the second derivative, you can find where you have points of inflection. And you should have at x equals 0. Second derivative changes sign. Right? At x equals 1 and at x equals 2. Get those? Yeah. Okay. Good enough? You got that? All right. So now we're going back to today. It's just graphing. Everything to do with graphing. Now I have a summary of here of what everything that each of the derivatives tells you about the graph. Okay? And you guys are very good with this. So we're going to take all that information and we're going to come up with a graph. We just want to have a few important points. You don't want everything to just be a guess. You notice, like when we did the do now, we had some real points to work with. We had 3. Well, when you're just coming up with a graph from scratch, you want to include like the x and the y-intercepts. You want to get the actual relative extrema. You want to plot those. The max and the min. You're going to have to figure out the y-coordinates there too. And the point of inflection or points of inflection. If you plot those points and you know the behavior on each of the intervals, you're going to come up with a beautiful graph. Right? I think it's going to be fun. I don't know. So this is a no calculator zone today, right? We're not even going to look at a calculator. Yeah? Sober's a rule breaker. Okay, so get the first derivative, and from that we should be able to determine the intervals where the function's increasing, decreasing, and where we have relative extrema. And if you want to do this sign chart, I have a sign chart underneath the graph. If you want to do the sign chart for it underneath, you can. Oops, don't look at that. Yeah, I have it there. Yeah, there is one. You don't have to put it down there. I just kind of like lining up the sign chart with the graph. I should close it. Okay, we're going to go over this now. Where's my little... That. Okay, so we're going to go over this one. You had to first get the first derivative. You should have 12x squared minus 24x. You find your critical values, and hopefully you got 0 and 2. And you made a sign chart for the first derivative, and the pattern was positive, negative, positive. You got that? Nice. All right, actually, let me just put that on mine. So at 0 and 2, this is exciting, right? 0 and 2. So when positive, negative. Well, I was trying to like line it up, make it look nice. Okay. Then you had to get your second derivative. That'll tell us all about the concavity. Come on. The second derivative is 24x minus 24. You set that equal to 0. You should have at 1. And you make your sign chart for your second derivative. Did you get negative, positive? Okay. I'm going to go back. Is that, no? Yeah. I thought I heard a, okay, so the second derivative sign chart right here. I can't even see these little lines. I'm just guessing. Was it negative then positive? All right, so that's at 1. This is 0, and this is 2. Okay, now we know basically where the function's increasing and decreasing from the sign of the first derivative. We know where the graph is concave up and concave down from the sign of the second derivative, but we need some actual points. So the points I'm suggesting that we get are the intercepts. So x-intercept, when you put in 0 for y and you solved for x by factoring, what did you pull out of 4x squared, x minus 3? What did you get for x when y was 0 and 3? So our x-intercepts are 0, 0, and 3, 0. Write them as points, your intercepts, okay? You don't want to write x equals 0 because it looks like a line. You know the y coordinate 0 of your x-intercepts. You just got to figure out the x. So let me plot those points. 0, 0, and 3, 0. 1, 2, 3. So this would be 1, 2, 3. Actually, I shouldn't plot them yet so that you always see where the points are so you know how to scale your axis. But the y-intercept you get by putting in 0 in for x. And if you put in 0 for x, what does y turn out to be? 0. So 0, 0, that point, the origin, is also our y-intercept. It's the only point. It can be an x-intercept and a y-intercept. Okay. Relative max. That's where the first derivative changes sign from positive to negative. Bless you. So that's at 0. We already know what we're going to get when we plug 0 into the function. 0. So 0, 0, you also have a max there. Relative min, that's where our first derivative changed sign from negative to positive. Where is that? At x equals 2. So our min is going to be, we're going to plot the point 2. And when you plug 2 into the original, what'd you guys get? Negative 16? Negative 16. Right? 4 times 2 cubed minus 12 times 2 squared. Point inflection, that's going to be at whatever x where the second derivative changes sign. What's the x-coordinate of the point of inflection? 1. If you plug 1 into the original function, what do we get? Negative 8. Now, since we want to actually fit all these points on our graph, if I make every box on the y-axis equal to 1, I'm not going to fit that important point there. So I'm just going to make every box 2. So this will be negative 2, as long as I label, negative 4, 6, 8, 10, 12, 14, 16. So it's okay if you have different number of boxes representing different lengths on the, as long as you're clear about it. So we have 2, negative 16. I got to plot the point 1, negative 8. I'll get over here. Our intercepts. Oh, I already have those down. So the key points, our intercepts are the 2, negative 16, the max, the 1, negative 8. And if you connected them right with the right shaped pieces according to the signs of the first and second derivative, it should look something like that. An uglier version of that? Yeah, I think I was going over it. It shouldn't be double lines though like that, but yeah, it should be increasing and concave down to, you have a max here at 0, 0. Then you have point of inflection at 1, -8. So it bends from concave down to up. You have a min at 2, -16. Back up, you got an x-intercept at 3, 0. X equals 3, and then it just keeps increasing. Get anything like that shape? Oh, all right. Now, the one you have for homework, if you flip the thing over, you have one problem. I got to tell you, well, and it's a pretty hard one because when you go to get the first derivative, let me see where. It's quotient rule. What? So when your derivative is a fraction, you're going to have to clean it up. Set the numerator equal to 0 and the denominator equal to 0. The one that says homework on the top. What's that?
I only got 0 as a critical point for that.
So you got yeah, you're going to have to distribute. Did you clean this up? Did you? So 2x to the 4. Oh, okay. Okay, yeah.
I don't know. That part there is when
okay.
I was doing the sign chart.
So you got 0. Okay.
That 0 was my only answer.
Yeah. Okay. And guys, remember, you can check if you're right with your graphing calculator. That's fine. I want you to make the connections, but do it without first and then check. Too fun. Bye.